Hi, everyone. My name is Vedant Misra. Thank you for coming. I'm going to be talking about deep learning for natural language processing at HubSpot. So I'll give you a quick overview of my background first. I studied physics and math at Columbia, focused on theoretical cosmology. Then I worked at a think tank called Nexi, focused on doing machine learning for banks and various government and intelligence institutions. Then I started a company called Kemvi. We were focused on natural language processing with information off the web to try to help sales and marketing teams customize and personalize their messaging using ML. And then we got acquired by HubSpot, which is where I work now, focused on machine learning for natural language processing at the intersection of research, engineering, and product. So I'll give you a quick overview of what Kemvi was doing and also kind of walk you through the life of someone in sales and marketing. So if you're a salesperson, your job is to get people to buy your stuff. And there are sort of breadcrumbs about your prospects all over the internet, bits and pieces of information about buyers and companies and products. And so if you're good at your job, you're going to read about your prospects and customize your messaging to get their attention when you send them content. And so what we were doing was that we built this distributed information extraction pipeline to pull information out of the web. So you can imagine if you're trying to sell to Ryan Levine, it's useful to know where he works. We're pulling that kind of information off of news articles, social media, press releases, etc. And then training language models on that data to try to customize people's messaging. What you're seeing here are a few snippets that are customized language to that recipient. So, I mean, the idea here is to capture people's attention, but the end state of something like this is this kind of failure mode, which we all have experienced. Something like 10 years ago, it was sufficient to put someone's first name in the subject line and they'd open your email 40% of the time. But now there are tons of companies that are focused on trying to help you customize the subject line, the messaging, the email, all of it to get you to open the email and to click on the link or reply or whatever it is. So, I mean, once you know how this stuff works, the magic goes away, which kind of turns this whole thing into an arms race. And so companies keep having to try to come up with better ways to capture people's attention. This is not a new idea. It's been going on for a long time, since the 90s, I mean, on the internet at least. And if you're selling anything on the internet, your funnel is basically as follows. You want to capture, in fact, if you're selling anything, you want to capture the awareness of your buyer, you want to get their interest, you want to get them to make a decision and eventually buy your thing. These are all a series of transactions that have to happen, getting them to open your email, click the link, download a white paper, give you information about them in a form, or whatever it is. And so right now, most companies will, if you want, you could buy a bunch of point solutions to solve this problem. You could buy Google Analytics, a CRM, WordPress, a whole bunch of different components. What HubSpot does is kind of build all of that stuff in one big stack. And so we're a quickly growing company with offices all over the world, making a bunch of money. And if you're doing machine learning in this context, this is how you feel, model all the things. And so we have a bunch of data from a bunch of different contexts about customers, because we kind of have the entire chain from when a seller learns about a potential buyer to when they actually buy. And so you can imagine the world as being this graph where every node is some agent in the world, and transactions happen once in a while. There's information moving between these nodes, and the big inference task is to predict sort of when are these transactions going to happen, and ideally, what do you say and when do you say it to get those transactions to happen. So I'm going to go through a little bit of our tech stack. So the data that we have, there's a lot of it, and of a variety of different kinds. Lives largely in Hadoop, SQL, and HBase. On top of SQL, we'll use Parquet. We use Kafka for streaming data. And this data takes various forms. It's call data, emails, blog posts, chats. And it's both generated by our customers and our customers' customers. And it's also a lot of entity data about stuff in the world. So data about companies and what they're doing and how big they are and how fast they're growing. And then also communication, which is chats between people. And so all of that data is used to train models in two ways. There's an automated training process, and there's also people who will train models. And it's kind of a combination of those things. We use scikit-learn, TensorFlow, PyTorch, primarily everything in Python to train models, and we do a lot of GPU compute. And once you have these models, the goal is to serve them in production. So we have a system called the inference server, which will receive featureized data from those data systems at inference time very quickly, and it'll serve up those trained models in production. And at the end of this, of course, you have HubSpot's customers and HubSpot's customers interfacing with these inferences. Cool. So what kinds of problems are we working on? So this is predictive lead scoring. The core problem here is what I kind of described earlier. Given information about all of the potential companies that could buy from you, who is likely to buy from you in a certain window? And so the way that you could cast this as an inference task is to say, what is the probability that a given contact will turn into a customer in some window? So you can choose that window, you can choose the parameters of this problem. It's an inherently difficult problem because you're trying to model this heterogeneous dynamic environment. You have very limited information, and there's huge variance across each sample because this is B2B sales. And so the process itself is governed entirely by the dynamics of people at the company. You don't have full transparency into what's happening there. And this is an example of the content strategy problem. So we help people write stuff on blogs. The nature of that task has changed considerably. It used to be sufficient to just write stuff that Google was going to rank, and you could predict that pretty well because it was the same thing for everybody. But now if you're like walking to work, you'll get different results on your phone from if you're at work, right? So it's completely customized to each individual and their context and tons of features. So it's a lot harder now to recommend what people should write about if they want to show up on search. And so the problem is much better cast as a machine learning problem than as a problem of trying to just rank on search. It's more about trying to find useful clusters of content in the text that you've produced to help people navigate through the information that you have in an effective way. And so what you're seeing here is the UI for a product where people punch in topics that they think matter to their buyers. And then our goal is to learn these clusters of topics and how they associate to each other. Got a couple of citations in the corner for things that we've tried here. Actually, a couple slides back, I have a couple of citations here as well. What I forgot to mention was what's really important with the predictive lead scoring problem for people is predictability, or explainability, I should say. So predictability is, they want the inference to be the same every time, given a certain amount of certain information. They want it to be deterministic. But explainability is, if you're telling me who I should sell to, your model better be right. And if it thinks it's right, can you tell me what it's thinking? I want to know why it thinks that. And so trying to introspect these models is very important. These are some citations on work on model explainability that we found pretty interesting. Yeah, so for the topic learning problem, we'll use a whole bunch of conventional sort of 90s approaches from David Bly et al., like LDA and stuff, and then also more popular current approaches like neural variational topic models. And through all of this stuff, we found it very, very useful to use pre-trained embeddings. There's a couple of citations here for Universal Sentence Encoder and for OpenAI's paper on generative pre-training. I'll get into a little more of that in a bit, but we found those techniques to be extremely useful. So this is the email list health model. This is actually something that was being worked on by Nicole, who's sitting in the back over there. The core problem here is that HubSpot customers send emails to a bunch of people. Some of them are bad actors. Some of them accidentally send emails to people who don't want to get them, but some of them are bad actors and send them deliberately to people who don't want to get them because they buy lists or whatever. And so we want to prevent people from doing that because if they send emails through our servers that bounce consistently, then our IP addresses get flagged, and that affects deliverability for all of our customers who are using the service properly. So we want to prevent people from sending spammy emails. Here's send time optimization. So the core problem here is to figure out when is the best time to send an email to someone to get them to open it. So the way you could cast this as an inference task is to try to predict the probability over the course of a day or over the course of a week that the email will be opened and all the features that you're feeding in. And naively, you could just take the mode of that distribution as the best time to send the email. But what we find in practice is that it's actually kind of tricky. Considering user behavior in the design of these products is always an important thing. You might suggest a time to send an email to someone that is not a time at which they want to have sent the email, even if it is automated. So for example, you might learn that if you send emails at 4 a.m. to a certain person, will always get there at 9 a.m. when they open their inbox, but maybe you don't want to send your emails at 4 because it's very clear that you weren't up before sending your emails. We also have a ton of chat data. So this is a screenshot of Growthbot, which is a conversational UI to structured data. There's two kinds of problems here. One is making new kinds of products that are conversational in nature, and the other is sort of supporting chat. Two different kinds of problems. Chat's very exciting data. It's synchronous. It's real time. It's human to human. We also have human to bot chat data, which is another kind of thing that we do. So there's a rich feed of real time information here on the things people want. And I'd say probably richest of all, or extremely rich, is call transcript data. So we just announced the transcriptions feature last inbound. But the truth of every deal is in the words that were said by the people on these calls. In that if a deal is going to happen, a sufficiently talented rep can tell from what was said, they're saying the right word. Maybe it takes a lot, but maybe you could figure out they're saying the right words, but they're not interested, right? But the information is there. And so the challenge here for HubSpot is to pull that information out of all of this text, which you can imagine is hidden not just in the text, but also the tone of what people are saying. But even before we get to the tone, there's a lot to do with just the text in terms of learning about what people are talking about, what they say that works, what they say that doesn't work, the spacing of the things people are saying, temporal features that affect the likelihood of deal closing, etc. Say you talk too much, right? The deal's not going to close because you're never asking questions. Cool. That's a quick overview of some of the technologies, some of the models that we have. Now I'm going to jump into the technologies that we're excited about that have been developed over the last year or so in NLP. So this is something that, unless you've been living under a rock, you should be familiar with. If you're doing any kind of NLP, these are sequence-to-sequence models, which were written up by, I think, Lewis Skever, Oriel Vinyals, and Clay and Google in 2014. The idea here is basically that you just have two components, an encoder and a decoder, both of which are RNN. You just feed in a sentence, and after you feed in the sentence, the RNN has a latent state that it's learned about that sentence, which is represented as a thought vector here. And then another RNN decodes a sentence from that thought vector. And so, this works fine, but the issue is that you can't learn information from a long distance away. So you can start reducing or you can start helping that issue by using LSTMs, other kind of core old technology that's still pretty popular. So these are workhorses of NLP, and they're going to be here for a while, but they have certain limitations. So one big issue with RNNs is that the latent space that you're learning doesn't have any useful structure. It's just what the LSTM is spitting out. And it's useful in that it's useful for minimizing the objective, but it's not useful in that you can't interpolate smoothly in that space. There's no useful structure in the space. And so there was some work coming out of the Bauman group and also at Amherst on using autoencoders with a variational constraint, so variational autoencoders. So to understand variational autoencoders, you have to understand autoencoders first. So the idea behind autoencoder is that you take some sentence, you feed it in through an RNN, you get some latent state, you then push it through a decoder, and your loss is set up so that you want the output to be identical to the input. So you have this information bottleneck in the middle that forces the network to learn a dense representation of your data. And so what they do on top of an autoencoder is that they force the latent space to look Gaussian, which is pretty useful because then you can interpolate linearly between 2 points after you've encoded them into latent space and get useful stuff out. So what does that look like? If you take if you take this sentence and you pass it through the encoder, and you take this sentence and you pass it through the encoder, and you get two latent vectors, and you interpolate linearly between them, and you decode those interpolations, you get grammatical sentences that conceptually linearly interpolate between those two ideas. And what you're seeing down here are these are 3 random sentences. They encoded them and they decoded them. This is just the mean of the posterior. It really decodes from the posterior samples. What you see here is that it's a long sentence. So this should be identical to this, right? It's a long sentence. It gets a little confused. The short sentence is still a little confused over there, but it's trying to get the gist of the sentence. So this is relatively old work. Relatively, it's a couple years old. This is an architecture that's kind of taking the NLP world by storm. So this is a transformer. This came out of Google in 2017, in July. This is Ashish Vaswani et al. And so the key interesting thing here is the use of scaled multi-head dot product attention. It's actually a pretty simple idea. It's just that the goal here is to attend simultaneously to both the information before and after the context that you're hiding in order to learn the observable use of representations. So there is no recurrence in this architecture. The way it works is that you just have this attention mechanism that learns a set of queries and keys over your encoded inputs, and the entire transformer encoder is pretty straightforward. It's just this multi-head attention object, and then up position-wise, fully connected feed-forward network, single layer. There's residual connections around both of these. So this is the transformer input block. They repeat this 6 times in their implementation. And the decoder is basically the same thing, except that because you don't want the sentence that's produced to be able to attend to be part of the sentence after the word you're producing now, if you're not supposed to know it yet, you just mask the output. So it's really a pretty simple thing, repeated 6 times here, 6 times here, and the reason this is compelling, so this is multi-head attention blown up, and you're doing in this case 8 scaled dot product attentions in parallel, concatenate all those outputs, and then interject them down dimensionality. The model just how to evolve in this case. So this architecture has completely taken the NLP world by storm. It's blown away every state of the art. And the main way in which it's proven useful is with embeddings. So I'll connect transformers and embeddings in a moment. So if you haven't heard of embeddings, the idea is, so an embedding is a vector that is a useful representation of some input data. Word2Vec was a big deal a couple of years ago because you can learn these vectors that encode semantic information about the ideas that you're feeding in. And so what's happening here is that the relationship between the vectors king and queen is the same as the relationship between the vectors man and woman. So you can do simple vector arithmetic and extract semantic information. So this is fine. This is useful. We've done a lot of good stuff with Word2Vec. But where the world has gone since here is toward learning embeddings for words from the hidden layers of models. So the first way this was done was with ELMO. This is work from the RNNs group. This is embeddings from language models. So basically, you just train 2 LSTMs, forward and backward, and you take the hidden layer, and you concatenate the forward with the backward hidden layer, and that becomes your embedding. So it's a rich representation of the word. The word is an LSTM hidden layer, richer than it would be for just skip-gram data sampling. That's what Word2Vec is. So that was great. That was the start of last year-ish. And then a team at OpenAI took it further by replacing LSTMs with transformers. These are all an LSTM, a transformer. This was kind of an obvious next step. And then another obvious next step was taken, obvious in retrospect, obviously, this is hard, was to attend simultaneously to the context both before and after the masked word, instead of just one at a time. And so once you do that, you get BERT, which is kind of the state of the art now for generative unsupervised pre-trained embeddings. And this is completely crushed every sort of benchmark for natural language inference and stuff. To give you an example, so this is a sample from Squad 2. The Squad task has to do with answering questions. It's a question answering task. So Squad 1, the goal was to, with Squad 1, they gave people a bunch of passages and they asked them to write up questions and answers to those passages. And the model had to learn. So people crushed that task within about a year. They did very well. And so they introduced Squad 2 last year, which was very similar. They gave people a bunch of passages. They asked them to write down a tough question, write down an answer. Also write down a question that looks like it could be answered from this passage, but has nothing to do with the passage. A distracted question. And then you feed these to the model, you don't tell the model which is which. And it needs to be able to tell you, no, I cannot answer this question. So it has to have an awareness of whether it can actually answer the question. Much harder problem. So you can see question 1, legitimate question. Question 2, not a legitimate question. It was the Bold Legal Protection Act of 1940. It has nothing to do with the 1937 treaty. But it's tricky, right? If you just skim this, you might get it wrong. Cool. This is Squad 2. Here's a leaderboard as of, let's see, September of last year, a few months ago. So you can see all these architectures, reinforced mnemonic reader, FusionNet, human performance as well above all this stuff. Exact match scores of 70, low 70s, for all the models, exact math score of humans of 86. And there's a screenshot I took today. So they're all BERT, and we've reached state of the art on Squad, basically, from the exact match perspective, and basically also from the F1 perspective. So yeah, BERT, amazing implementation, very useful pre-trained weights that anyone can just go download and use, and quickly achieve state-of-the-art performance in a variety of tests. So where do we go from here? So this is an implementation from Facebook that came out of the Jason Weston's group. The paper is called The Wizard of Wikipedia. And so what they do is that they ask two people to have conversations, and they give them access to Wikipedia. And you're supposed to use only information on Wikipedia to have this fake conversation. When they train a model, they give the model access to Wikipedia, and they give it with this lookup structure. They give this, this sort of lookup information retrieval system that it can use to find an article and pick a sentence out of that article. So how does it work? This is a sample from their model, which we can just read out. So the topic is ebook. The model gets this. The human says, I don't know why, but I've never gotten into ebooks. The model says, same here. I have a Kindle, but I don't use it for ebooks. It's nicer to hold a real book and turn pages. The human says, yes, I like the physical feel and smell of a real book. The model says, I actually had an ebook where you got to download the ebook after selecting it online. I grew out of it. I prefer paper books also. So it goes on, right? But this is astonishing performance. It's grammatical, it's consistent, it remembers what it said, and it's nothing like the chatbot, the RNN-based chatbots of just 3-4 years ago. Right? We were doing character RNN chatbots 4 years ago, and now this is the stuff that's happening. I think that's it for transformers. I might have. Oh no, this is another transformer paper. So the task here is, okay, so the cool thing about transformers is that in principle, you can attend to an arbitrarily long input. So you could feed this thing a book. You could ask it a question at the end, like the first sentence, and if it's trained, it's converged, in principle, it can answer that question. And it has to do with the way that the positional encoding mechanism works in the transformers. It's very, very clever. So the point is, you're constrained not by the architecture, but by memory. And so people are trying to push the limit in terms of trying to figure out how to modify this architecture so you can feed in very, very long inputs. And so in this paper, this is a team out of Google, they modify the self-attention mechanism in a few ways. One of them is to pass your keys and values through convolution to reach dimensionality. Another is to just split up your query keys and values a priori and then merge them again. Don't fully understand how to do that. But, before I show you this, the task is, you give the model the text of all of the pages cited by a Wikipedia page. And you don't give it the Wikipedia page. You ask it to predict the Wikipedia page. Okay, so generate a Wikipedia page from all the pages that it has cited. Very complex information retrieval task, tons and tons of pages, right? Lots of stuff to attend to over long distances. The top sample is machine generated. Dewey and LaBeouf LLP is an international law firm headquartered in New York City, formed in October 2007 through the combination of these two companies. And it's hired approximately 1,300 partners. It goes on. This is all factually correct. It's actually pulling this stuff out and it's producing a useful, correct Wikipedia page, which is pretty astonishing. I think that's it for me. Thank you. Yes.
What are the typical sizes of some of these models? Just like number of parameters. Yes.
Yeah, so as a couple of examples, BERT base is 110 million parameters, BERT large is like 350 million, something like that.
Just curious, how do you get all the data for the HubSpot models? Like, for example, when the email, how do you collect all the data?
So the question was, how do we collect all of the data on when emails are open and all the activities and stuff? The answer is very meticulously. We're doing it for a very long time. That's kind of the whole point of the system. So it was built from the ground up to do that. Should you be scared? Yes. I mean, every time you're opening your, every time you do anything on the internet. So I'll give you a scary example. The frontier is always moving. It is now a feature in many chat systems on websites for the party that you're chatting with to get a live feed of your keystrokes, which is a huge invasion of privacy. It feels like to the average consumer, but they present it as a feature. It's like it's a live instant preview. And so sometimes, the curtain falls down because the person answers the question right after you send it, and it's a very complex question. It's clear they've been looking at this all along, and there's an article, I think, in the Consumerist or whatever about this, and someone's pretty pissed off. So yes, so technology keeps pushing the frontier in terms of how much information it's pulling out of you. So that is something to be aware of and probably scared of. And just be aware of it for sure, so that you're more deliberate about it. When it comes to knowing about email open times and stuff, the mechanism there is pretty simple. It's just it's pixel tracking. So if you block all images, you can block that. But I mean, that's just the tip of the iceberg.
Let's go back to that third model. It's actually quite fascinating. You actually depend on any training data that's actually labeled.
So the question is, what are the labels that are used to train BERT?
Right.
Yeah. So all these mechanisms, they implement unsupervised generative training. What that means is they use what's called the closed task, which is where you take some sentence, you mask a word, and you ask the model to predict the word. So you have your labels by virtue of just having some large corpus, because you're making your labels on the fly. And so once you have this set of weights that effectively captures transition probabilities in English language, you can train it. If you now have labels for some tasks, say you have a bunch of strings and then a bunch of 0, 1 for some tasks, sentiment or whatever, now you can train for a supervised objective from that pre-trained checkpoint. So you can start from a very useful place if you want to encode text, and you're much more likely to convert to a useful model.
So this is depend on some sort of topology on space for the training stuff.
Oh yeah, so the pre-training is done on a huge corpus of just multilingual text, multilingual in fact. And so this is another, I should mention, a crazy aspect of modern models. There's a version of BERT that's multilingual. It's trained on like 70 different languages. You can do the word-to-vec semantic stuff on the hidden space of that language across languages. So you can encode, you can do king minus man plus woman in like Japanese, Tagalog, and Hindi, and it'll work. And even larger stuff. So yeah, it's not a specific like ontology or corpus that it's pre-trained on. It's just pre-trained on a huge amount of stuff that a bunch of Google engineers decided it would be useful to use.
My question is more about like the pipeline, because it seems like you're very on top of all the new research on NLP, but you also have a job and you have to keep your production or system running. So I was curious, like how much do you get, how easy it is to transfer to your agro production running, and then there's a new paper that completely changes everything. So what's the process that for you to implement a new thing and actually test and put on production?
It's a very, very good question. So the question had to do with how do we put models in production, and what is our iteration time like when new research comes out? The answer is it's very, very easy to put models in production. And the reason is that the architecture of the system is basically such that the process of deploying a new model is nothing more than pushing some code and trained weights to a certain location. So where was my architecture diagram? Here. So basically all you need is another one of these guys. And so the issue in putting this thing into production is not so much deploying the model, which has been made easy by a very large number of very talented engineers who've been working on stuff for a while. So we've got a big infrastructure for inference at scale, and for automatic training and for pulling data out of systems and all this stuff. I guess the issues in putting stuff into production, new research into production, always come from differences between the data that stuff is pre-trained on and our data. Defining a model in a useful way from the perspective of a product problem that we actually have, And then all the sort of product issues that fall out of that. What's it going to look like? How's it going to work? What's the feedback going to be? All that stuff. And then obviously training time, implementation time, that sort of stuff. But it's not really a pipeline issue. It's more just getting the thing up and running.
So systems like Gmail are trying to distinguish real emails from not so real emails, right? And so they're following up behind you, right? Because they're presumably attempting to detect emails like yours and saying, not real, put in the spam file. Right? How rapidly do the two systems track each other? You have to change yours every month, for instance, because nothing will get through after a month.
That's a good question. So the question was how quickly are spam filters adapting to your attempts to capture people's attention? So HubSpot neatly sidesteps this entire boondoggle. And the way they do this is by, the whole mission of the company is to try to sell to people in a sustainable way, in a way that they want to be sold to. So we actually don't make any products that let you upload a list. We actively make it hard for you to upload a list. So most of the time, our emails don't get flagged as spam by the recipient. It's because they actually are considering buying that thing, or one of those things, and they want to get the emails. They don't love them. No one loves these emails, right? But they are fine getting them in their inbox and keeping an eye on the prices or whatever. But it's usually not that adversarial of a relationship with the recipient. That said, there are certainly contexts where there is an actual arms race between senders and people who are trying to reduce volume. It definitely plays a role with spammers and phishers more so than with people trying to sell stuff. Selling stuff is really pretty far down, I think, Google's list of grievances with people sending emails.
Thank you.
Thank you so much.